Good afternoon, ladies and gentlemen. My name is Noriaki Nakayamada of NuFlare technology. And my presentation title today is Conquering Heat Issues in E-beam Lithography, Past, Present, and the Future. So I will give you, main topic is about resist heating issue. And I will give you a quick tour of reviewing how we've been coping with these heat issues in the past and how we are planning to solve it today and what the situation will be like in future. So heat has been a precious resource. This Greek god Prometheus gave fire to the mankind. And heat has been an important resource for us to survive in the dark and cold ice age. And heat is also an essential resource for everybody to live a cultural life. So tonight, they are going to serve you a lot of various kinds of foods for dinner. But without heat, you can taste only sashimi, not even sushi, because sushi needs steamed rice. But too much heat can be also a serious threat for our species. The most famous example is global warming, changing the climate of this globe and causing many natural disasters. And when looking at our own industry, a similar thing can be said to some extent. Heat is also an important resource in the microfabrication. So this is a very simplified mechanism of a classic type chemically amplified resist. And the heat is playing a key important roles in two steps. First is the incident electron, heat or the energy of the electrons working on the photoacid generator to create source acids. And in the second step, the heat from the baking tool will accelerate the chain reactions of acids, decomposing the dissolution inhibitor to make this portion dissolved in the development process later. But again, too much heat is problematic. These pictures were taken from the paper of Abe of Toshiba by then, and with NuFlare technology now, published in 1988. The resist is PMMA, and of course it's not chemical amplified resist type, but it also has a heating issues by a deterioration of polymers at a very high temperature. And if too much dose is given one time, the shape of the shot is deformed in a rounded shape, and the CD error was exceeding 100 nanometer. And this is kind of worst case in heating issues. And it can be easily avoided by choosing appropriate dose for one time. But there will be another issue still remaining. That is proximity heating. So left image, animation is showing the writing order and temperature rise in a microsecond scale. And first, center main pattern is written first, then surrounding serif and then surrounding SRAF patterns are exposed. And the right picture is the captured temperature rise at the time of shot being exposed. And color coding is blue is coolest and red is hottest. And in this case, the first center box is written first, so there will be no heat transfer from the previous shots. So it has coolest temperature. But right next to this main pattern, this upper left serif pattern gets the highest temperature because of the heat transfer from this center box. So the proximity heating effect is the, in our case, in our lithography versions of Inconvenient Truth we have to face. So let's look at how we've been coping with heat issues in the past. This is again old data taken from our old EBM 3000 written on ZEP 7000 at 10 microcoulomb per square centimeter by 1 pass. And this is an image of underdeveloped, half-developed image. And the color gradient is showing the remained resist thickness variation. Bright is thinner and darker is thicker. And we placed metrology sites at the 4 corners of the subfield and measured the line width. And this is a result. For the ZEP resist, the CD error was exceeding 10 nanometer. And by using a chemical amplifier resist, it was mitigated to some extent, but we still see some effect. And by increasing the pass count from 1 pass to 4 pass, all resist, the CD error was reduced. So the solution number 1 is to increase the pass count. There are other approaches to mitigate the heating effect. First one is a well-spaced writing order by changing and controlling the subfield writing order, like 1, 2, 3, 4, 5, 7, 4, 6, and 7, and so on. And this is a paper from Babi-san in this room, published in 2003. And the other approach is called alternate subfield writing order, proposed by Goto-san from Geo. And subfield writing order is like checkerboard style, skipping one subfield, another, and then coming back to the skipped subfield and continue expose the full pattern. And they both made a certain level of success. And now I am going to explain the solution we are going to propose for our most recent VSB mask writer. So the situation is getting worse and worse. The exposure dose is getting higher and higher. Back in the early 2000s, the exposure dose you were using were below 10 microcoulomb. But in the early 2000s, later 2000s, the exposure dose was over 10 microcoulomb and below 15 microcoulomb range. In the early 2010s, it increased up to 15 microcoulomb to 20 microcoulomb. And now, in 2015, the exposure dose is going to exceed the 20 microcoulomb. So the resist sensitivity is same as ZEP 7000. So it's back to non-chemical amplified resist error. And write time is also getting longer. So we cannot easily increase the pass count to cope with the heating issue. So we have to decide and come up with a solution number 2 to correct the resist heating effect. But there is a difficulty in correcting heating effect. That's why the effect itself has been known for many years, but nobody has succeeded in the correction. I will explain the why. So the write time is, this is a familiar formula to estimate the write time, is shot count times exposure dose divided by electron current density plus positioning time times multiplied by pass count plus overhead. So it is essentially proportional to the shot count. But for the heating calculation, the cost is proportional to square of shot count, because you have to sum the heat transfer from all the previously written shots. So the calculation cost becomes 1 plus 2 plus 3 plus up to n minus 1, resulting n times n minus 1 divided by 2. So it is essentially proportional to square of shot count. So the correction calculation time can rapidly take over the write time. This is the difficulty of heating effect correction. So we propose two solutions. First, solution 2.1 is to correct by tertiary field, not by shot basis. In EBM 8000 or earlier, the subfield position is also almost random. So you have to calculate the heat transfer from randomly appearing shots for one shot by another. And that made problem solved very difficult. But from EBM 9000 or upper machine, we have tertiary field, and most of the shots are grouped in a tertiary field. So the calculation would be easier. And the other benefit is the count of tertiary field is fixed once the die size is fixed. So it's easier to estimate the worst case or longest case of correction time. The other solution we are going to propose is the adoption of GPU technology. And from next model of EBM, each EBM machine comes with this super high class server over tens of worker nodes and several hundreds of GPU chips, and even more, several hundreds of CPU cores. And the total calculation performance is about 350 teraflops. And comparing this, the supercomputer K achieved 10 petaflops in 2012. Of course, this is double precision number and this is single precision number, so you cannot directly compare. But now EBM machine is going to have mini-scaled supercomputer per each from next platform. And that's a huge investment, you may say. So we have to prove that it's worth spending that money. So we will give you two kinds of benefits. One is CD accuracy benefits, and the other is write time benefit. And for the CD benefit, this is the correlation between estimated temperature rise versus measured CD. And if you apply some correction model, the CD accuracy or error gets down by 60% of the original error. So it will give you about 60% CD error reduction. And for the write time side, by going from 4-pass to 2-pass, we can reduce the shot positioning time. You cannot, unfortunately, reduce the exposure time because resist sensitivity is fixed. Regardless of the pass count, you need to give such electrons to make resist exposed. But by going from 4-pass to 2-pass, the write time will be decreased by about 20%. So that it's worth approximately 1/5 of the total cost of EBM machine, plus CD accuracy improvement by over 60%. And for more detail, there are two papers in this PMJ 2015. First one is oral session tomorrow, starting from 11:50, session number 4-3 by Suganuma of a NuFlare technology titled Correction of Resist Heating Effect on VSB Mask Writer. And the second one is poster session, the same day tomorrow, from 5:25, poster 7B-1 by Nomura, study on modeling of resist heating effect, correction in EB mask writer EBM 9000. So both two people are attending this workshop, so please contact them if you have any questions beforehand. And now I will give you some prospect for the future. And as most of you already imagined, the solution is multi-beam. So multi-beam technology is believed to bring the situation back to old peaceful days by its low current per beamlet and increased bus count. So this is the simulated temperature effect rise or heating effect. And this is an emulation of writing sequence. But you can see, or you may not see, the heating issue in a multi-beam case. And the good thing about multi-beam is that we don't have to argue which company's logo to be written first. Because two logos are written in parallel. So multi-beam will not cause any heat between the companies. And yeah, it brings peace to everybody. But I said everybody, but I bet some members in this room will argue and claim that multi-beam is not future, it's reality today. So I may have to give some prospect for further in future when customer requests even shorter write time with even higher exposure dose, then it may be necessary to come up with a solution or a correction, even on the multi-beam platform. But as long as we carefully choose the electron current and the path count, we may not need heating effect correction on multi-beam platform for certain time period. I bet it will be 5 years. We don't need heating correction on multi-beam system. So that's all I prepared for today. Conclusion. NuFlare and D2S have developed resist heating correction system. And this technology brings benefits in both better CD control and higher throughput with reduced path count. And resist heating effect has been present since the beginning of E-beam lithography for over 30 years, but its correction has been finally realized by the power of GPU cluster. And we will introduce this new correction for E-beam 9500 and E-beam 9000 upgrade from this year. Thank you for your attention.